This time we're going to talk about the parabolic equation, and it's one of our most versatile tools for doing sound propagation modeling, especially at low frequencies. Often frequencies of most interest in terms of ship noise and broadband sources that propagate long ranges. So we can have a 2D, we can have a 3D parabolic equation. We can have elastic boundaries. We can have a medium that's all elastic. We can have arbitrary sound speed profile, dependence in depth and range. So very versatile tool. And we start with the Helmholtz equation in cylindrical coordinates. So we're talking about r theta, of course, r phi z. And we can write for a harmonic time-dependent source. We'll get dp dr squared plus 1 over r dp dr plus dp dz squared. Then we'll have our k squared term. I'm going to write that as k naught squared n squared p, where k naught is equal to omega over c naught. C is a reference sound speed. K naught will be the reference wave number. So let me title this reference wave number. And n, of course, is going to remind you of earlier lectures, the index of refraction. And we'll define that as c naught over c r z, same way we would in optics. And of course, this gives us k is equal to k naught n. So we're going to assume azimuthal symmetry. For this particular case, we're going to look at just a 2D. We already are looking at just a 2D case here. Oops. And we're going to rewrite the Helmholtz equation as an operator. So let's define capital P d by dr, capital Q as n squared plus, 1 over k naught squared d by dz squared. Okay. We're going to assume the solution is of the form p of rz, little p of rz, is equal to psi of rz and the Hankel function k naught r. So should be pretty comfortable assumption now. We're really talking about an outgoing cylindrical wave. So most of the range dependence will be taken care of in that second term. In terms of the kind of geometric spreading range dependence, we're going to take care of the range dependence introduced by the environment in that first term, the psi term. Okay. We're also going to assume that psi r of z varies slowly in range. What exactly does that mean? The metric here we're talking about is really relative to the wavelength. Okay. But in general, not really a problem in the ocean at low frequency. Okay. We already know that the definition of our Hankel function, which is to refresh. So solution to the Bessel's equation. In other words, if you take d by dr squared of it in cylindrical, and then you take k squared times that, you get 0. Okay. And of course, we had a nice asymptotic expansion. I'll cram this in the corner. When we looked at normal modes, we had for k naught r greater than 1, k naught r was about equal to root 2 over pi k naught r e to the I k naught r minus pi over 4. Okay, really crammed into the corner, but you can go back and look at the lecture on normal modes to recall that asymptotic expansion, or you can just look it up on the internet. Wow, it's a great age we live in. Okay, so we sub this into Helmholtz, our bipart solution. Bipart solution. And so we have d psi by dr squared it's 2 d by dr Hankel plus 1 over r d psi dr plus d psi dz squared plus k naught n squared now minus 1. That equals 0 times psi equals 0. So now if we take the assumption that k naught r is greater than 1, this reduces to simply d psi dr squared plus 2I k naught d psi dr plus d psi dz squared plus k naught n squared minus 1 times psi equals 0. Okay? Now we plug in operators. P and Q, and we get P squared plus 2I k naught P Okay. So now we want to factor this, right? We have this nice quadratic form. Let's factor this into outgoing and incoming parts, right? So obviously we're going to have P plus I k naught minus I k naught Q times P plus I k naught plus I k naught Q. And then to make things balance, we're going to have I k naught commutator of P and Q, psi equals 0. If it's been a while since you've done a quantum mechanics course, P commutator of PQ on psi is PQ psi minus QP psi. Okay? This is commutator of the operators. Okay? Now, let's just look at the outgoing term. And this is a key assumption to keep in mind when you think about the results from this code. We're really just going to be looking at forward propagating energy. We're never going to deal with stuff that's scattering back and resolving the complete field in that sense. So if we look at that, we have this equation P psi I k naught q minus 1 psi. Or d psi dr equals I k naught square root of n squared plus 1 over k naught squared d by dz squared minus 1 acting on psi. Okay? So what is this? This is a one-way wave equation. It's first order. And we can obtain a solution for this which depends on how we approximate Q. Depending on how or this square root, this tricky little square root here. Okay. Now, there have been numerous assumptions so far in our development. So let's just recap. So far, we have assumed, wow, my writing is getting worse every day. We've assumed we're in far field, right? We took the far field approximation of our Hankel function. We've assumed commutation is negligible. And no back propagating energy. Okay. And our last hurdle is how we approximate Q. So there's a number of different approaches to this and some significant advancement over the last 10 years or so. But I'm just going to follow the classics. Okay. How do we approximate Q? Well, it's a square root, so there's going to be some approximations that jump instantly to mind. So let's expand it by first defining, let's say epsilon is equal to n squared minus 1. Mu is equal to 1 over k naught d squared by dz squared, and small q is equal to epsilon plus mu. So big Q is now equal to 1 plus Q. So basically at this point you say, you can't stop yourself from saying if the absolute value of Q is less than 1, use Taylor series expansion. in which case Q is simply 1 plus little q over 2, whoops, minus q squared over 8 plus q cubed over 16 minus dot dot dot. And you can see that basically you're just including higher and higher order derivatives with regard to derivative squared with, or powers of derivatives with regard to z, okay? But the real question is, how good is our assumption? Is q less than 1 satisfied? Well, let's start with a solution we know. Consider plane wave. Right? If psi were just e to the I kr plus or minus kz z. Well, we know that k is equal to kz squared plus kr squared, square root of that, and sine of theta is equal to plus or minus kz over k. This is the angle of propagation. So mu is then given by minus kz squared, k naught squared equals minus n squared sine squared theta. And Snell's law makes a return, is defined by cos theta naught cos theta. That's how you get your index of refraction. So Q equals epsilon plus mu, as we defined, equals n squared minus 1 minus n squared sine squared theta is now going to equal minus sine theta naught when the dust settles, okay? So, very interesting. Q is only a function of the source radiation angle. Oops. Theta naught. So for horizontally propagating waves, little q really is small. The small q is small. Thus q equals to 1 plus q over 2. Let's leave it at just that, which is equal to 1 plus n squared minus 1, 2, plus 1 over 2 k naught squared is true for horizontal the propagating energy. So for long range problems, this approximation should suffice, okay? And that's indeed the first way that this that the PE parabolic equation code was implemented. So how can we improve? So I'm going to say higher angle propagation. So what if we need to resolve things that propagate higher angles, not just horizontal stuff? Well, there's another approximation of a square root like this. we can say that it's A naught plus A1 over Q, B naught, B1 plus Q. And then we choose the A's and B's to minimize error. Given the angle of interest. This works well for theta naught less than 40 degrees. So that kind of opens up what we're talking about. The most popular way to approximate Q is the Parabolic series. And that's where square root of 1 plus Q is equal to 1 plus the sum of AJM over Q plus BJM over Q plus order Q to the 2M plus 1. Whoops. Terms. So we can choose the upper order of our sum to reduce the error. But what are the AJs? Okay. Oops. Well, what are the AJs and BJs? AJM is 2 over 2m plus 1 sine squared over j capital pi 2m plus 1. BJ is cos squared j pi 2m plus 1. And with m equal to 5, you can satisfy angles up to 90 degrees. So now we have d psi dr is equal to I k naught. Oops. J equals 1 to m. AJ's n squared minus 1 plus 1 over k naught squared d by dz squared. All over 1 plus bjm n squared minus 1 plus 1 over k naught squared d by dz squared psi. Okay. Solvable using finite difference. Finite element methods. Same thing we did for computing the mode shapes, right? Now, there's been some improvement since then, and that is known as the split step this is for a uniform medium. In other words, epsilon equals 0. We can say we have our 1 plus q. Now 1 plus mu plus epsilon equals 1 plus mu plus 1 plus epsilon minus 1. Oops. So we can rearrange this. Let's rearrange this and write minus 1, 1 plus epsilon, 1 plus mu. And we can increase efficiency. 1 plus q, 1 plus mu plus epsilon, by including even more terms. Whoops. Epsilon 1 plus mu as we had before, but now we're going to say minus 1 plus 1 plus mu minus 1 plus epsilon all over 2. And a second term minus 1 plus mu minus 1 plus epsilon all over 2. And then we expand 1 plus mu and 1 plus epsilon as Pade series independently. Okay, pretty straightforward. In principle, in practice, can get a little messy, but it's not so bad when you look at the code. And really what we're doing is we're solving the one-way equation in range marching. So we update our range as we propagate the energy. So you may recall back a few pages ago that on the right-hand side of our equation we had 0. So I need to write here, this only marches the field forward. There's no source. This doesn't solve field. It only marches the field forward. So we must generate a source field or use a starter. So keeping with this sort of historical theme, people started by just sort of saying their field was going to have some Gaussian with their source there, and then they would march that field forward. And generally, we use a self-starter. Which is to find a modal solution for the source type, so depending on the source band, radiation pattern. But I have written here in my notes, the Gaussian source is common. Since it takes no computational power. Okay. Obviously has limited angle. Drawn. Right, so it's not going to radiate necessarily the way a real source would. You're going to miss out on high energy information, but it is simple to code up. Now, since this is one of the last methods we're looking at in this course, I'm not going to ask you to code this, but we'll use some existing code, and the PE code is always sort of evolving. But I hope that gives you a bit of a background of some of the important assumptions and limitations that go into PE. And one thing, of course, that's important is we talked about essentially how the wavelength is the unit of measure. And it really is the unit of measure for the marching as well, the marching of the field. So as you go to higher and higher frequencies, your range resolution has to increase more and more, and it doesn't just slow the code down in a linear way, it slows the code down in an exponential way. So this is really a low, still, even with all the computing power we have, still really a low frequency solution. I'd say sub 1 kilohertz on most computers. All right, that's it for now. Thanks.